Today we're going to talk about water and its importance in biological systems and in organisms. To begin with, we're going to talk just a little bit about chemical bonding. Now, for about 100 years, we've had an understanding about how an atom looks. We have a very dense nucleus. In fact, about 98-99% of the mass of an atom is found in the nucleus. And we know that it is surrounded by electrons. This is the famous Bohr model, which sort of has a cloud of electrons around a nucleus. Oftentimes we see this, but we don't get the real scale. Imagine that we were the size of an atomic nucleus. An electron would be the size of a small bird. So imagine a sparrow. And the distance between the nucleus and the electrons is immense. In fact, we find that an atom is mostly empty space. In our analogy, that would be a sparrow circling us at a distance of 2 miles. So hard to get that little scale in a little drawing like this. The other thing that's different from a true atom compared to our Bohr model is that the electrons are in specific orbits around the nucleus. They're not so much like a particular cloud like that you see here. These small orbits are called orbitals. And there are several different types of orbitals. Some of them look very strange. There's some that look like dumbbells, other ones that sort of look like a sphere. And for every orbital, we can hold 2 electrons. So 2 electrons in every orbital. Now, the very interesting thing about these electrons is that electrons can hold energy. We'll find out a lot about that when we go and look at how energy is harvested from cells, or from food for cells. And we'll see that a lot of that energy comes from electrons. And electrons can store energy as an energy of position. And a lot of that energy is translated or understood by being in different orbitals. Let me show you what I mean by that. For example, if we look at the 2 electrons that are closest to the nucleus, they are going to be found in an orbit that we call the first orbital. Right? And you can see it here in the left part of the graphic. Down below, you'll also notice that we can represent the same thing as what we call an energy shell. That energy shell, these 2 electrons, they are in the orbital closest to the nucleus, and it also translates that these have the lowest amount of energy. Those electrons that have the least amount of energy are going to be closest to the nucleus, and they're going to be in that first, what we call energy shell. We also have additional orbits that are outside of that. All right. So in this case, you can see we have a second orbital. This is the 2s orbital. This holds also 2 electrons. And then you also notice that we have this strange one. That's actually a combination of 3 orbitals. We have a 2p orbital. You can see that it is sort of a dumbbell. So if you follow the x-axis, it has a dumbbell shape. Then there's one on the y-axis. All right, that's called another 2p orbital. And then there's a third 2p orbital that's on the z-axis. Each one of those can hold 2 electrons. So if you go and you look at those particular orbitals and you count them up, you'll notice that you end up with 8. So that second orbital can actually go and hold 8 electrons. And those 8 electrons are a little bit farther away from the nucleus. And what that means is that they also have more energy than the ones that are closest to the nucleus in the lowest energy shell. So that second set of orbitals can hold 8. So in that case, we say that that energy shell has 8. And if you look at the figure on the right, you can see how they stack up when you combine the first and the second one. You end up with energy shell that has 2 electrons, and the second energy cell which has 8. And it usually goes on like this for a couple of more shells in that same 8 in the outer orbital. Now we have a name for that energy shell. We call that the valence shell. So the electrons that are found in the valence shell have the highest energy of the electrons that orbit the nucleus. Now, when we go and we take a look at the periodic table, you might recognize this as a periodic table. Right? The periodic table is arranged by the number of protons that are found in the nucleus. And so this is what we call the atomic number. So hydrogen, you see up in the upper left, which is represented by an H, has just a single proton in the nucleus. That's the most common form. And it has 1 electron. Usually we find that atoms of different elements are going to be electrically balanced. So they have an equal number of protons and electrons. If you go down and look at the bottom left, you can actually see our next one, which is helium. Helium has 2 protons and 2 electrons, but you'll notice that its shell, its energy shell, that orbital, is filled. You'll notice that it has 2 electrons in that energy shell. If you follow down that column, helium, neon, argon, krypton, xenon, and radon, those are all classified as the noble gases. Noble gases are described as being chemically unreactive or chemically inert. They don't react with anything. You'll never see anything like helium dioxide or neon dichloride or anything like that. They don't react with any other element. Right? There's a reason for that. It turns out there is an idea in chemistry that works very well. Right? It's the idea of what we call the octet rule. Right? Atoms, in order to be stable, really want to have their valence shells filled. Right? So if you have the outermost shell filled with the maximum number of electrons that's available, then you become a noble gas. Once you have your valence shells filled, then you don't have to go and interact with any other element. So this is why helium, neon, argon, krypton, xenon, and radon are chemically inert. And if you look at the energy shells that are on the bottom of the graphic here, you can see that indeed all of them have the octet rule filled. So helium has 2, it doesn't need any more. Neon has 2 in the first shell, 8 in the second. It has its valence shell filled. Argon, again, you can see 2 in the first, 8 in the second, 8 in the third. Its valence shell is filled, and so on and so forth. And you can see Ernest Rutherford down here on the bottom right, famous physicist that discovered the nucleus of the atom. He said, in chemical compounds, atoms tend to have the electron configuration of a noble gas, we find that the entire left side of the periodic table, so if you start with the noble gases, everything to the left of the noble gases do not have filled valence shells, and they will bond and chemically react with other elements to go and get the same configuration as the noble gases. They'll try to get their valence shells filled. And that's where chemical bonding comes from. It's the strategy of these different elements, atoms of these different elements, to become like a noble gas, to get their valence shells filled, to fulfill the octet rule. Now, an easy way to fulfill the octet rule and kind of be like a noble gas is to share electrons. So here's an example. This is hydrogen. Hydrogen, we know, has one proton and one electron. That's the most common form. And it has a problem. It would really like to have a second electron to fill that orbital, to fill that valence shell. So it does that in a variety of different ways. One way is just to go and bond with another hydrogen atom. This particular hydrogen atom is in the same situation. It needs another electron to fill the valence shell. So what they do is kind of ingenious. They form molecular hydrogen. Molecular hydrogen is just two atoms of hydrogen, and they do it by sharing electrons. By sharing a pair of electrons, now they both have filled valence shells. Right? Now, when atoms share electrons, we call that covalence. Think about the word valence. Valence is the outermost shell of an atom. And so covalence, oftentimes when you think about co-captains or co-pilots, all right, they are working together to perform a particular job. They're sharing power. They're sharing responsibility. So in this case, they're sharing a valence shell. And this is kind of interesting. How they share these is that the electrons spend part of their time around the nucleus of one atom in the bond, and the other half of the time spent around the other nucleus. That's what we mean by sharing. So those electrons, that pair of electrons, is spending part of their time around one hydrogen nucleus and the other half spinning around the other. And so we call this a covalent bond. Among the chemical bonds, this is by far the strongest. And we like covalent bonds because the covalent bonds are the ones that we find primarily in biological molecules. When we look at carbohydrates and fats and steroids and proteins and nucleic acids like DNA and RNA, we find that all those organic compounds are held together by covalent bonds. Now you might be wondering about the single. Molecular hydrogen has what we call a single covalent bond. And what that refers to is that it is sharing a single pair of electrons. Right? So a single pair of electrons. Right? Pair doesn't really sound like single, but think about a couple other things where a pair really is just one thing. If you wear a pair of pants, that's just one pants. Or a pair of scissors, that's just one scissors. Right? So in this case, when we share a pair of electrons, that's a single bond. So in this case, we call that a single covalent bond. Now, there's a couple ways to represent this. You'll notice on the bottom of the graphic, we have H2. You'll notice we have a little diagram. And you also notice on the right-hand side, we have two H's separated by a single dash. That single dash tells us that that is indeed a single covalent bond. Now, we don't have to stop at just sharing one single pair of electrons. We can share more than one pair. Here's a great example. About 22% of our atmosphere is oxygen. And most of the oxygen is found in this form. This is called molecular oxygen. It's two oxygen atoms that are bonded together by covalent bonds. Now, oxygen has a slightly less filled covalent shell. Excuse me, a valence shell. If you look at oxygen, it has 8 protons. That's what makes it oxygen. It is electrically balanced, so it has 8 electrons. And if you look, you'll notice it has 2 electrons in the first shell. All right, that one's filled. But it only has 6 in the valence shell. It would really like to have 2 more. 2 more would make it like a noble gas and fulfill the octet rule. So, it really needs 2 more. So, it finds another oxygen atom. And in this case, what they do is they share 2 pairs of electrons. Hence the name a double covalent bond. Share 2 pairs of electrons. And just like that, all of a sudden, by their sharing, they now have fulfilled the octet rule. They now have the configuration of a noble gas. And again, what we mean by covalent is that these electrons are spending half their time orbiting one nucleus and half their time orbiting the other nucleus. Right? And so in this case, this is how molecular oxygen works. And you can see how we represented on the right with the 2 dashed lines. That tells us that is a double covalent bond. So in this case, we're sharing 2 pairs of electrons. Now, we don't have to stop at 2. We have one more where we can share 3 pairs of electrons. And a good example of that is a major component of the atmosphere, and that is going to be nitrogen. Nitrogen gas makes up most of our atmosphere. Roughly about 3/4 of our atmosphere is made up of nitrogen gas. Nitrogen has 7 protons and 7 electrons, so it's electrically balanced. It has 2 electrons in the first shell, so that's filled, but only 5 electrons in the second shell. It would really like to have, excuse me, 8. So each nitrogen needs 3 more electrons to fulfill the octet rule. So, in this case, when it bonds to another nitrogen and they share 3 pairs of electrons, we call that a triple, 3 pairs, covalent bond. A triple covalent bond. So in this case, just like the other ones, those shared electrons are spending half their time orbiting one nucleus and half the time orbiting the other nucleus. And we call this molecular nitrogen. So we can have single covalent bonds, double covalent bonds, and triple covalent bonds. There is another type of chemical bond that is found among elements, and it's what's known as an ionic bond. If you've wondered about what the heck an ion is an ion is an atom or a molecule that has a charge to it. Remember, I mentioned that a lot of atoms of elements have an equal number of protons and electrons. Well, sometimes atoms of elements will lose an electron. Electrons have a negative charge. When you lose an electron, all of a sudden the electrical balance is off. The number of electrons doesn't equal the number of protons. And so you get an overall positive charge. We call that type a positive ion or a cation. Now, you can also have situations where you have an atom of an element that gains an electron. In that case, if we look at the number of protons versus the number of electrons, the number of positive charges is less than the number of negative charges. And that atom becomes negatively charged. We call that a negative ion or an anion. You may have heard those words before. Now, ionic bonds are formed by the electrostatic attraction between positive and negative. One of the forces in our universe is this electrostatic attraction. In fact, when we look at negative electrons and positive protons, that's what keeps the atom together. It's that electrostatic charge, that positive and negative. In the same way, an ionic bond forms when we have a positive ion and a negative ion that are electrically attracted to each other. Now, an ionic bond is not going to be as strong as covalent bond. All right? So, when it comes to chemical bonds, this one is described as having less strength than a covalent bond. Oftentimes, things that are ionically bonded, we describe them as being a salt. Right? So, we often think about table salt, sodium chloride, but there are a lot of different salts out there. And those salts, technically, are all going to be held together by ionic bonds. Now, the formation of ionic bond is actually kind of interesting because it leads us back to understanding this process of trying to get and fulfill the octet rule. Now, sodium, which is clear on the left side of the periodic table, has just a single electron in its valence shell, its outermost shell. For it to get a noble gas configuration, for it to fulfill the octet rule, it would have to get 7 more electrons. That is a pretty tall order. So it does something really brilliant. It gives up an electron. By giving up an electron, then you'll notice that all of a sudden its valence shell, which is the one below it, is now filled. It has 8. So it has fulfilled the octet rule by giving up an electron. Now, you'll notice that chlorine, right, is in a different situation. It has 7 electrons in the valence shell. It just needs 1 more. It's just short 1. So chlorine just needs to grab 1 extra electron. And since sodium often gives them away, right, chlorine will take them up. And so by accepting an electron, chlorine now fulfills its octet rule. By losing an electron, sodium becomes positively charged. By gaining an electron, chlorine now becomes negatively charged. In fact, chlorine, when it becomes an ion, we use the word chloride, a chloride ion. Now, the electrostatic attraction between them, the positive and negative charges, hold them together and form an ionic bond. Now, since ions have a charge to them, whether they're positive charge or negatively charged, they will also conduct an electric current. And since they conduct an electric current or form an electric current when they move, we sometimes describe them as electrolytes. So when you hear the word electrolyte, just think, oh, those are ions. We're talking about ions. Okay, now that we've known just a little bit about chemical bonding, we're going to start looking at water. Now, water is incredibly important for living organisms. In fact, without water, our planet would pretty much be uninhabited and hard to be uninhabitable. Water has modified the temperature. It is a fantastic heat sink. It keeps the temperature fluctuations in check. It's a great medium for locomotion. It has some wonderful buoyancy. It's a fantastic solvent that dissolves things, and it freezes in a very, very strange way that we'll talk a little bit about. If we look at living organisms, we find that we are largely composed of water. In fact, if we look at the average human body, about 55% water. The average adult male is about 60% water. And the average adult female is about 50% water. Males have a little bit more water because they have more muscle tissue, and muscle tissue holds more water. And they generally have less fat. There's less water in fat than there is in muscle tissue, and that's why there's a difference there. The average adult male weighs about 80 kilograms. That's about 176 pounds. And the water content of 60% would be about 48 kilograms or 48 liters of water, equal to 8 cases of standard size bottled water. So we are mostly water. In fact, where is all that water located? You'll notice that 90% of your lungs is water. Of course, your blood is a lot of water. Your skin, about 80% water. Muscle, 75% water. Your brain is pretty watery, about 70%. Even your bones, which we often think about as dry and lifeless, are 22% water. So we are filled with water. In fact, our cells are filled with water. We have fluid, we have water surrounding our cells. We're pretty wet creatures. And that kind of makes sense. We're terrestrial animals. And if we look at the early history of the Earth, we find that everything began in water. We only became terrestrial within the last 400 to 500 million years. And that's really a challenge. If you're a terrestrial animal or a terrestrial plant or a terrestrial critter, one of your big problems is actually preventing dehydration, or what we call desiccation. And we have a lot of different ways for us to do that. Alrighty. So let's talk a little bit about the water molecule. This is our water molecule. This is H2O. H stands for hydrogen, so we have 2 hydrogen atoms and an oxygen atom. If you look at the hydrogen, as you know, just has 1 proton, the most common type, and it has 1 electron. So it really needs 1 more electron to fill its valence shell. Oxygen, on the other hand, as you know, has 8 protons and 8 electrons. So it has 2 electrons in the lowest shell, and it has 6 electrons in the valence shell. It just needs 2 more to fulfill the octet rule. So it does a unique thing. It actually goes and forms 2 covalent bonds, one with each hydrogen. Right? So each hydrogen shares a pair of electrons with the oxygen. Right? So we have what we call a single covalent bond joining the hydrogens with the oxygens. Right? Now, you'll notice that they're a little bit at an angle. In fact, if we go and we measure the angle between the two hydrogens and the oxygen, it kind of looks from this diagram that that'd be about 90 degrees. Well, turns out that it's a little wider than that. It's about 104.5 degrees. So, kind of forms like a little V shape. Right? Now, something really, really interesting happens. You might notice that there's some strange little Greek letters. Right? That Greek letter that you're seeing on either side of the water molecule is the lowercase for delta. Delta looks like a triangle. It's the fourth letter in the Greek alphabet. You have alpha, beta, gamma, delta. This is what the lowercase delta looks like. Right? So you'll notice on one side, on the oxygen side, we have two of those little deltas with a minus sign next to them. And on the hydrogen side, you'll see lowercase delta with a plus sign behind it. Right? Now, you probably recognize and say, well, that's positive and negative charges. But the delta tells us that it's not a full negative, like giving up an electron, negative. And it's not a full positive, like taking, or excuse me, a full negative, like it's taking on an electron, or a full positive as giving up an electron. That delta represents a partial charge. So a partial positive and a partial negative. Now, let me explain a little bit about why that is the way it is. And we're going to go back and look at the periodic table. Now, we've seen how the periodic table looks. We have our noble gases on the right. Everything else on the left is reactive to be like a noble gas. But I want to show you another periodic table, and this one is organized according to a principle called electronegativity. Electronegativity is a measure of how attractive the atoms of an element are to electrons. So electronegativity is a measure of the attraction of an element to electrons. We have some that are just loved by electrons. Electrons just want to hang out with these atoms, whereas other ones, not so much. Now, it's measured on a scale from 0 to 4. So let me show you this picture here. And as you can see, we have our periodic table, but it's arranged slightly different. It's arranged by electronegativity. You'll notice here on the left, we have things like francium and cesium, all right? Sodium and potassium all have electronegativity less than 1. That means they're not very attractive to electrons. Electrons don't really find them all that appealing and don't want to spend a lot of time with them. But you'll notice that it gradually increases as we go to the right. And you'll notice that the highest one is fluorine. Fluorine has electronegativity of 4.0. That's the maximum. Turns out the fluorine atom, electrons absolutely love. It is super attractive to electrons. Electrons just love to hang around fluorine. You'll notice that the second one, the second highest one, is oxygen. All right. Oxygen has an electronegativity of 3.5. That's still pretty high. electrons absolutely love oxygen. And because they like oxygen a lot, they're going to go and try to spend as much time with it as possible. So oxygen has a super high electronegativity. But remember, in water, we also have hydrogen. So let's take a look at where hydrogen is. And you'll notice that hydrogen is hiding out a little bit to the left. And you'll notice that it has an electronegativity of 2.1. 2.1, which is not bad, but compared to 3.5, it's pretty weak when it comes to attraction. So this difference in electronegativity, this difference in how attractive electrons are to the atoms of a given element, will have a big influence on how those electrons are shared in a covalent bond. Let's take a look at our model again. It turns out that when we look at our covalent bonds here, shared between oxygen and hydrogen, we find out that those electrons are not going to be equally shared. I mentioned before, so if we look at hydrogen, for example, molecular hydrogen, those electrons are going to be equally shared. That single pair of electrons is going to spend exactly half their time around the nucleus of one hydrogen and half their time around the other. It's like perfect joint custody, all right? Equal time. Same with molecular oxygen, all right? Oxygen has they're sharing two pairs of electrons, all right? They have the same electronegativity, and so those electrons are going to spend equal time. They're going to be equal shared between those two atoms. When you get two elements that form a chemical bond, a covalent bond, where there is a big significant difference in electronegativity, then you get this unequal sharing of electrons. And what happens with water is that since oxygen has a much higher electronegativity, the electrons spend more time orbiting oxygen than they do hydrogen. Right? It's not equally shared. Those electrons are unequally shared. Now, since electrons have a negative charge, and they're spending more time around an oxygen atom, that means that on one side of the water molecule, on the oxygen side, this is going to form a negative pole. And you can see it over here. You can see a little, since there's electrons have a negative charge and they're spending more time around the oxygen, on one side of the molecule, we have an area that has a slight negative charge. Now, since the electrons are spending less time around the hydrogen, you'll notice that on the hydrogen side, there is a slight positive charge. And that's because electrons are spending less time around there. So that side gets a slight positive charge. Right? So you start looking at water and you go, oh, look at that. It has basically 4 poles. It has 2 slight positives around the hydrogen, and you'll see 2 slight negatives around the oxygen. Right? So we have water is described as a polar molecule, right? Because it has one side that has a slight positive, one side that has a slight negative. Right? And because of the unequal sharing of electrons, we call the covalent bond, we call that a polar covalent bond. Now, to be technical, we would describe that as a single polar covalent bond. They're sharing a single pair of electrons. Right? This is polar, which means unequal sharing of electrons. All right, so single polar covalent bonds. Now, how would you describe something like molecular hydrogen? Well, you would also call it a single covalent bond, but because they are equally shared, we call it a nonpolar covalent bond. So molecular oxygen, molecular nitrogen, molecular hydrogen, where the electrons are equally shared, we call that nonpolar covalent bonds. So water is this strange molecule. It's what we describe as a polar molecule. And it has a charge to it. It's not a full charge, but it has a partial charge. And if you remember, we have one of the major forces in the universe is this electrostatic attraction. Now, because of this polar nature of water, it gives it some very, very unique properties. And since water is a polar molecule, it can go and bond with other polar molecules like itself. So here, let's imagine that we have a little water molecule, and we get another water molecule. Let's say it's oriented correctly. Right? They come in contact with each other. And we get a slight positive side and a slight negative side come in close proximity to each other. Now, electrostatic attraction is going to hold them together, and it forms a type of bond. Polar molecules will go and form a chemical bond that is known as a hydrogen bond. So water will stick to other water molecules by this hydrogen bond. Now, we saw that an ionic bond is held together by a full positive and a full negative. If you're just bonded by a partial positive and a partial negative, that bond is going to be much weaker. And compared to a covalent bond where you're sharing electrons, it's going to be weaker still. So in this case, our hydrogen bond is the weakest of the three major bonds. In fact, it is only 1/20th of the strength of a covalent bond. So this one is much easier to break than we might have with an ionic bond or a covalent bond. Hydrogen bonds are found everywhere. We find lots and lots of hydrogen bonds. Right? Lots of polar molecules out there. In fact, because of its hydrogen bonding and because of its polar nature, a single water molecule can form hydrogen bonds with 4 other water molecules. You can see in this one little picture here, the dots, we saw how the dashed lines represent covalent bonds. When we represent a hydrogen bond, we go and use a little dot, all right, a dotted line or a dotted line. As you can see, because a water molecule has 2 positive ends and 2 negative ends, it can go and form hydrogen bonds between them. So you can see a hydrogen end going and bonding to an oxygen end. You can see an oxygen end binding to a hydrogen end. So water molecules can go and bond with 4 other water molecules at the same time. Now, there are plenty of other molecules that have this unequal sharing that has this polar covalent bonds that make them polar molecules. Here's an easy one. This is a common one. This is ammonia. Ammonia is nitrogen plus 3 hydrogens, and there is a significant difference in electronegativity between nitrogen and hydrogen. So around the nitrogen, you actually have 3 slight negative charges. And around the 3 hydrogens, you have 3 slight positive charges. And this is why ammonia dissolves so well in water, because it's a polar molecule, and it forms hydrogen bonds easily with water, which is also a polar molecule. We have lots of other ones that are nonpolar. For example, if we look at hydrocarbons, if we look at methane and ethane and propane, all right, butane, a lot of organic compounds have carbon and hydrogen. In fact, if we look at fats and oils, for example, we'll find that they pretty much are mostly just carbons and hydrogens. Now, if you look on the periodic table, electronegativity, you'll notice that the hydrocarbons, the carbons and the hydrogen are fairly close when it comes to their electronegativity. Carbon just is a little bit more attractive, but it doesn't make any difference. So anytime you have a bond between a carbon and a hydrogen, it's going to be a covalent bond, and it's going to be nonpolar. Those electrons are pretty much equally shared. So anything that is pretty much all carbon and hydrogen, not going to be polar, not going to form any type of hydrogen bond at all. So in this little picture here, you can see ethane, which is just carbon and hydrogen. The black part of the molecule are carbon atoms, and the white ones are hydrogen atoms. Below that is a fat, and as you can see, it's mostly carbons and hydrogen. It turns out that this is also a nonpolar molecule. Carbon dioxide, which is a gas that we breathe out. It's one of the products of metabolism, also classified as a nonpolar molecule. And of course, things like molecular oxygen, molecular hydrogen. Anytime that you have things that bond to themselves, you know, their electronegativity are going to be the same, and so going to be nonpolar. All right. Now, let's talk a little bit about some of the properties that makes water unique. One interesting thing about water is that because it's a polar molecule, it is a fantastic organizer. And what we mean by an organizer is that anything that is nonpolar. So if we have, for example, some nonpolar molecules in water, water will sort of force them together, that they hang out together, that water goes and excludes them and puts them in their own little position, in their own little area. And this is what we call hydrophobic exclusion. Hydrophobic means fear of water. Nonpolar molecules do not mix with water. Think about oil and water. They don't mix. Think about getting butter on your hands and trying to wash it off without soap. It just stays on there. Right? So this turns out to be interesting when we start looking at particularly things like cell membranes, things like proteins. We're going to find that they are using this polarity and non-polarity of molecules and using water as a way to organize complicated things. Things like boundaries of cells and internal boundaries within cells, right? All based on this idea of hydrophobic exclusion. Okay. So, we're going to talk a little bit about some of the properties of water that are created by this polar nature. And some of these are pretty wild. One very unique thing about water is that by all standards, it really should be a gas at room temperature. Chemically and physically, because of its size, at room temperature, it really should always stay a gas. It's remarkable, absolutely remarkable, that it is a liquid at such a high temperature. Now, water as a molecule is a very, very small molecule. Usually we find that the smaller the molecule, the lower the boiling point. Right? Let's take a look at hydrogen gas, molecular hydrogen. Hydrogen is an incredibly small molecule, so it only has one proton. And in molecular hydrogen, we have two atoms, each with just a single proton. And of course, it's going to stay a gas most of the time. In fact, as you can see, in order for it to become a liquid, we have to go below the boiling point. So for liquid hydrogen, all right, that has to be less than minus 252 degrees centigrade or Celsius. That's really, really cold. Right? You might have played with liquid nitrogen. Liquid nitrogen, all right, is a common thing that you see in science demonstrations. Right? One of the coolest things I've seen is with liquid nitrogen is taking an inner tube from a bicycle, putting it in there and taking it out, and it just shatters. That's just amazing, watching rubber shatter, just like plastic or glass. But liquid nitrogen, to stay liquid, has to be below minus 195 degrees Celsius. Oxygen, which is a little bigger, is a liquid at below 182 degrees Celsius. If you've ever played with dry ice, that's what frozen carbon dioxide is. And carbon dioxide, in this case, for it to actually go and be, in this case, a solid, it has to be less than minus 78. Now, water, take a look at the molecular weight. It's 18. Right? It has a boiling point of 100 degrees Celsius. That's 212 Fahrenheit. What that means is that below that temperature, water is a liquid. And of course, we know that below 32 degrees Fahrenheit or 0 degrees Celsius, it's a solid. So compared to its size, if you look, it should have a boiling point somewhere between 252 and 195, somewhere between hydrogen and nitrogen. In fact, as you can see, it's less than around 200. So for all intents and purposes, water is weird. It really should be a gas at room temperature. It should have a very, very low boiling point, a boiling point around minus 200 degrees Celsius. In fact, just to kind of show you, I made a simple little graph and took a picture of it. And as you can see, based on our little prediction, we would expect that water should really be around between 200 and 250, minus 200 and minus 250 degrees Celsius. But because water is polar, and that's the big thing, is because water is polar, it has a much higher boiling point. Because water is sticky, because it forms hydrogen bonds, it's much more difficult for the water molecule to actually go and break free. When we say something becomes a gas, what we mean by that is that an individual molecule has broken free. Now remember, water is held by 4 other water molecules. And they're each holding on to that water molecule. Now, even though that grip is small, when you have multiple bonds, that's harder to break. That water molecule has to vibrate a lot to break those bonds to become an individual molecule. And when it becomes an individual, then it becomes a gas. Right? It's almost like having 4 friends. You know, one person grabs one arm, one person grabs another arm, one person grabs your leg, another person grabs the other leg, and you try to break free. And they're constantly going, and, you know, you break free, they grab you again. You know, you break free an arm, they grab it again. Break free a leg, they grab it again. It takes a lot of energy to actually go and escape from that. And the same things happen with water. Since water is polar, it has to overcome that electrostatic attraction to become an individual water molecule. And that's what we call a gas. That's the state of a gas. So water is very weird, and it's because of its polar nature. Water is often described as a powerful solvent. When I was a student, they used to describe it as a universal solvent, and that it was thought that it dissolved more substances than any other substance on the planet. Right? Water, because of its polar nature, will bond and form hydrogen bonds with anything that is polar or has a charge to it. So things like ions do really, really well in water. They dissolve in water. Things that are ionically bonded dissolve very, very well in water. For example, we know that salt dissolves very, very well in water. In fact, when we put sodium chloride, table salt, into water, a very interesting thing happens. Remember, what's holding those sodium and chlorine atoms together is an ionic bond. It's electrostatic attraction between a positive and negative charge. What happens when it gets into water is that the water molecules start to form shells around them. They start to go and surround them and form what are called hydration shells. Now, since sodium has a positive charge, right, the water will actually go and surround it with the oxygen side. The oxygen side, as you know, has a slight negative. And so if you look at the little diagram, you say, oh, look at that. All the little negative sides are going and surrounding and bonding the sodium. Same with the chloride ion. It has a negative charge, so it's the hydrogen side, and you can see all the little hydrogen sides going and bonding to it. It completely surrounds these two ions. So when you have salt water, that's what you have. You have all these ions, sodium ions and chloride ions, that are surrounded by water, and they form these hydration shells. Remember, hydro just means water, so shells of water. Now, it doesn't necessarily have to be something like something that's a salt, like things that are ionically bonded. Anything that has a charge or anything that is polar. And another thing we like to dissolve in water is sugar. Right? Now, up in the upper left, you see a sugar molecule. Right? This is actually a sugar molecule, glucose, which is one of the sugars you find in table sugar. This is also blood sugar, and blood sugar, as you know, dissolves very well in the blood. We're always transporting blood sugar. In fact, at any given time, on average, we have about 90 milligrams of blood sugar for every 100 milliliters of blood in our bodies. The reason that things like glucose dissolve so well in water, which is most of our bloodstream, is because of an interesting little functional group. You'll notice that there is a little functional group in the diagram up there called the hydroxyl group. Oftentimes, carbohydrates, like sugars, will often have a little functional group, something that is common within their molecules. In this case, we see that it's an oxygen and a hydrogen. That is described as a hydroxyl group. And it turns out hydroxyl groups, because you have a covalent bond between an oxygen and a hydrogen, that's an unequal sharing of electrons. The electrons like to spend more time around the oxygen, less time around the hydrogen, so we get a partial positive charge near the hydrogen and a partial negative charge near the oxygen. And because that, it's polar. Those hydroxyl groups are polar. And so water loves to stick to them. This is actually why sugar dissolves so well in water. It's because we get a little hydration shell around the molecule because of these hydroxyl groups. Now, we can go and make something that's insoluble, we can make something that's nonpolar into something polar by adding a hydroxyl group. In fact, this is often how your liver will go and get rid of, bad things. We often hear about detoxifying, all right? Your liver does that all the time. You don't need to go and get a cleanse or anything like that. Your liver and your kidneys do all that work for you. So one way the liver does it is just simply by adding hydroxyl groups to certain types of substances and molecules that the body wants to get rid of. And by adding those hydroxyl groups, it makes it a lot more water soluble and easier to flush out in the urinary system. For example, here on the left, you'll notice that we have a gas. We have methane. And methane, because it's a hydrocarbon, which is carbon and hydrogen, is nonpolar. It's a nonpolar molecule. Because it's a nonpolar molecule, all right, it does not mix with water. Methane gas does not mix with water. But we can make it water soluble by replacing one of the hydrogens with a hydroxyl group. And we turn it into an alcohol. This is methanol. This is wood alcohol. All right? And it is soluble in water now that it has a hydroxyl group. Because water is polar and likes to stick to other polar things like itself, we say that water is very sticky. It sticks to itself. We call that cohesion. So when water sticks to itself, cohesion. In fact, cohesion is sort of like binding to like. Right? Adhesion is when unlike substances bind. Right? So, for example, when you go and take a shower or get in a bathtub or go swimming and your skin gets wet, the water is adhering to your skin. Your skin is covered by polar molecules or molecules that have a charge. That's the only reason water sticks to you. All right? If your skin was completely nonpolar, all right, you could get in the shower, come out, and you'd be completely dry. The water would just bead right off of you. Right? This is oftentimes why we wax our cars, because we don't want our cars to get wet. All right? Water is a powerful solvent, and it can actually go and eat away at the metal that we find in cars. So we often go and put a protective non-polar layer of wax on it so that it becomes unwettable. Right? Now, because of this cohesion and adhesion, water does some remarkable things. One remarkable thing is that it can undo what's called capillary action. You might notice that when you go get your blood tested, sometimes when you go and get your blood tested, they'll do a little finger prick. Well, they'll puncture one of your fingers, and they'll get a little blood sample. And they take a little glass tube, stick it on there, and you might notice that the blood rushes up into the tube. Right? We often call that a capillary tube, and it's an easy way to go and get a sample to test your cholesterol and your triglyceride levels, also to go and test your hematocrit levels, how many red blood cells you have, all right, whether you're anemic or not. Why does the blood actually go up? Well, it's a little thing called capillary action. You can simulate it in much the same way with different thickness of straws. You'll notice on this little picture here on the right, we have a very skinny straw, very skinny tube. And then as we go to the left, the diameter of the tubes get bigger. And you'll notice that on the one on the right, the water has gone up the tube, and it actually is above the water level. And as we go to the left, you'll notice that the water doesn't go up as high. What's going on here is a combination of cohesion and adhesion. Now we know that water sticks to itself, right? So water is cohering to itself, right? So inside the tube, in the middle of the tube, you've got water molecules that are joined to each other. But they're joined also to water molecules that are adhering to the insides of the tube, to the walls of the tube. Right? And it's almost like mountain climbers. Let's say that you're climbing a mountain and you have one friend that's holding on to you. You know, you're giving a piggyback ride up this cliff face. All right? Now, it's difficult on its own just to go and do that, but, you know, let's imagine you're a really good mountain climber. So with one person, that's not too bad. You can climb the mountain. But let's imagine you start adding 2, 3, 4, 5, 6 people to your back. You're not going to be able to climb as far because you've got more hangers on. And that's what happens with greater diameter tubes. When you have a small tube, the ratio of hangers on to the ones who are climbing is much, much smaller than the ones with a big tube where you have few climbers and a lot of hangers on. And that's what happens. So this is why in tiny tubes, the water creeps up farther. It's because you have more climbers and less passengers. Right? The passengers are stuck together to each other, the climbers are on the side, and that electrostatic attraction is greater than gravity and they can creep up. So the smaller the tube, the higher the water will go, which was figured out a long time ago by plants. Plants discovered that, especially a terrestrial plant, if you're a terrestrial plant, your biggest problems are, number one, gravity. All right. So if you look back in the history of the world, all right, most everything started out in the water where you don't have to worry about gravity too much. Everything's buoyant and you're surrounded by water. But once you got on dry land, all of a sudden you have to deal with gravity and you have to deal with drying out. So if you're a plant, how do you get water from the soil up to the top of the plant? You can use capillary action. And if you go and you look at vascular plants and you make a section through them, you'll see that it's composed of a bunch of tiny tubes. Right? These tubes are called xylem. Right? These are vessels. And they're tubes that are microscopic. Think about the tiniest straw you've seen. All right? Now shrink that down a dozen times. And you've got the xylem vessels that you find in a vascular plant. And so because of that, the water can move up from the soil up into the plant. Now, it can only go a certain level. Right? With that, we have to go and add another help. And that other physical help is what we call evaporation. Now, let me show you how a plant works. This is a phenomenon that's called transpiration. Water goes and enters into the plant by the roots. Now, roots are covered in tiny little hairs. It increases the surface area for absorption. All right. So the water goes and enters through these tiny little root hairs and enters into these xylem vessels. Right? So capillary action is bringing those up. Now, inside that plant, as that plant gets taller and taller and taller, we have a column of water inside those xylem vessels. And as the plant gets taller and taller, all right, we know that plants have to use water for photosynthesis and for other things. All right? And so they have to go and they start giving off oxygen. All right? The other thing, too, is certain parts of the plants are pretty leaky. Right? If you look at a leaf, which is really the organ of photosynthesis for a plant, on the bottom of the leaf, on the underside, you have these little holes. These are called stomata. Right? And these stomata are important because they actually go and bring in the CO2 and release the oxygen as a waste product from photosynthesis. So they're necessary to get the gases into it. But they also, because they're holes, allow water to seep out, to evaporate out. So we have a combination of evaporation and capillary action. So we have this big column of water, and as the water evaporates out the stomata, right, it pulls on the column. So we're getting pushed from the bottom and pulled from the top. And as the water evaporates, it's replaced like a conveyor belt. So more water comes in, more water leaves at the top. Now, this is a remarkable process. If you look out at our green world, and if you look at a big tree, let's say we have a big, 100-foot tree, that tree is probably going and absorbing, right, let's say 100 gallons of water every hour. 100 gallons of water is going up that tree and evaporating out every water in complete silence. We're looking at huge amounts of transpiration that are taking place in vascular plants. Now, capillary action is also found in a variety of other things too. If you've ever used a paper towel, if you've ever used a napkin, right? If you've ever used a sponge, you know they're incredibly absorbent. And there's a reason why water is absorbed by them. Instead of having little tiny tubes, they have little tiny spaces. And just like a little tiny tube, as long as there's a charge or polar molecules lining those, water will go against gravity and seep up. One of the coolest places is to actually go and look at the beach. If you go to the beach, you'll notice that above the water line, if you go and you dig down, you're going to find that the sand is moist. Turns out the reason that that sand is moist is because of capillary action. Water is moving up into little spaces between the sand grains. Right? And it has electrostatic attraction to the molecules and atoms that are on the surface of the sand grains. And so water creeps up and actually produces a pretty wild habitat. One of our big undiscovered places, unexplored places, where we actually found a whole new phylum of animal in the early 80s, was at that little area, that little moist area above the water line. We found a whole new phylum of animal there, living in there, a perfectly wet little spot. Okay, let me go ahead and stop there. We'll go on to part 2 on our next video, and we'll see you later.